here. So today we're going to talk about photochemistry. So we're class 10, photochemistry. Okay, 1 second. Okay, so let's start with the most famous example. Of course, we all know that in nature we have the sun, and the sun is irradiating the earth. Okay, this is my poor attempt to draw the earth. And we receive a lot of UV irradiation from the sun, but that's actually good. We are also protected by the ozone layer, right? And on the earth, as you all know, we have nice little plants, and those plants do photosynthesis. So photosynthesis is, of course, one of the best and oldest photochemical processes that are around. And people in man-made structures now also use a lot of photochemistry. And we haven't touched on this topic at all. So it's quite an interesting new direction that we'll take today. So we're going to talk about artificial systems. Okay. And we're going to split, well, not really split, but there are two aspects that are kind of intertwined in photochemistry, right? One is photophysical processes, and one is photochemical processes. And they are intertwined, right? It's hard to completely separate them. So photophysical processes, you can think of excitation, fluorescence, etc. Okay, and we'll come to those processes a bit later. Photochemical processes, so the definition is a chemical change brought about light. Brought about means caused. It's just a fancy way of saying caused. And typically we use wavelengths of 100 to 700 nanometer, right? So from deep UV to red, or sometimes even new red. What's the main difference between photophysical and photochemical? Photophysical processes are mostly reversible, right? You can excite the molecule, it can fluoresce, it goes back to the ground state. No harm done, typically. Photochemical processes are mostly irreversible. So we make, the cool thing is we make new chemical species. Okay, so what are some features of photochemical reactions? Well, first, of course, the most important event is we need the absorption of a photon. And that leads to, that leads to an excited state. Okay, so there are many other states or other possibilities. To get an excited state, which we won't discuss in this course, but you can do electric discharge. We can do in a flame. If you've ever done atomic absorption spectroscopy, then you know that this is possible if you spray things in a flame. You have ionizing radiation, or we can have excitation by a chemical reaction. So that is called chemiluminescence. So luminescence means it emits light, and chemi means chemically induced. So chemiluminescence, the very famous compound is luminol, which reacts with peroxide, if I'm right, to give light emission without excitation, right? So chemically induced. Okay, so we're going to talk about absorptions of a photon because it's the most common and the most convenient. And typically, we'll come back to this later, it's extremely fast, right? 10 to the minus 15 seconds. Okay, so you'll see that a lot of those photophysical processes are extremely fast. The photochemical processes are typically a bit slower. Okay, so this is maybe a bit of repetition of what you already know, but let's look at a molecular orbital diagram. Okay, so it's typically something like this. Let me try to do this nicely. Okay, so we have, for example, the ground state. Okay. This is the benefit of doing it on a tablet. Oops. Why not? So I'm just going to copy this 3 times. If it doesn't, okay, whatever. Okay, we'll fix this. Come on. Okay, just imagine that is straight. I'll fix that in the final slides. So we have the ground state, right, with all the orbitals filled. And we have the singlet excited state. So one electron is here. And we have the triplet excited state. We'll get back to that a bit later. Okay, so you see in the triplet state that these electrons, so this one and this one, are in the same direction. So they're actually repulsive. So the triplet state is energetically less favorable than the singlet state. And it's also formed indirectly. So it's impossible when you promote an electron to the first excited state that you also flip the spin of that electron. So a triplet state has to be made indirectly, and we'll see that is with intersystem crossing. But we'll get back to that. Okay, so there are some laws, not as hard as in thermodynamics, but let's call them laws of photochemistry. Okay, so the first law is the Groth-Hughes-Draper law. And that says that only light absorbed by a molecule can be effective in bringing about chemical change. So that sounds a bit stupid, right? Of course, a molecule has to be involved, otherwise, nothing will happen. But actually, in practice, many times people carry out a photochemical reaction and they don't get any product. And then turns out that sometimes the glassware or the solvent can also absorb. Yeah. And typically this is below 200 nanometers. So I believe that water starts really seriously absorbing at like 180 nanometers. So if you want to do a photochemical reaction in water at 150 nanometers, it's never going to work. Or if you use simple glassware like you use in the lab, that has a cutoff, I don't know exactly the number, but somewhere around 300 nanometers. So if you want to do with UV reactions, you need to use quartz cuvettes or quartz glassware. So that's, let's say, the most, the first thing to keep in mind when you do photochemistry. The second law is the Stark-Einstein law. And that says that the primary photochemical act involves the absorption of just one photon, right? So excitation, one photon promotes one excitation. There are, of course, some exceptions. And that is when you use lasers. So lasers are extremely bright. And with lasers, you can have 2 photon or more, even 3 photon processes. So for those of you who have also my lab on a chip course, I told you that you can do 2 photon photolithography. So very briefly, right? So if we have a ground state and the first excited state, normally you just get a photon that is absorbed and you get the transition. So in a 2 photon process, we have, so this would be the excited state, this would be the ground state, and this is what's called a virtual state. And for example, if this transition with normal excitation would be 350 nanometer, you would need 2 photons of roughly double the wavelength. So 2 times 700 nanometer, about 700. It's not exactly double, but more or less it's double the frequency. Because with light, the energy, so shorter wavelengths, is more energetic, right? More to the UV, more energetic light, more to the red, less energetic. Okay. So let's look at some very basic thermodynamical considerations. Okay, so let's look at free energy diagram. Okay, so we put the Gibbs free energy here, and we would draw some states. So imagine we have a substrate and we have a product. And so this is the ground state of the substrate, the ground state of the product, and this would be the first excited state of the substrate. So you can imagine if I do a thermal reaction and I want to go from the substrate ground state and I want to go here, this of course is thermodynamically unfavorable because I have to go up in Gibbs free energy. On top there's probably a kinetic barrier, right, with a certain activation. So thermally, this process will not happen. But if we first, so we start here, if we first excite to the first excited state, then we have, again, there will be a kinetic barrier, but like for all processes, right, we have an energetically downhill process, which is spontaneous because it's going down in Gibbs free energy from the excited state, and this is going to be irreversible, as we'll see later. So it's impossible to go from the ground state of a product back to the excited state of a substrate. So that leads to some advantages. Right? So if we excite a molecule, it is more energetic. So that means it's faster, the reaction is faster. But it also means we have a wider range of possible reactions. And that also then means that we can make more different products. Okay, what's also interesting, we won't go in that in a lot of detail, but for example, the photoreaction of alkenes, it gives the opposite stereochemistry compared to thermal reactions. So that's quite weird, right? Other advantages. So molecules in the excited state, they are better donors and better acceptor, which is weird. They have, if you look at the ionization potential, so the ionization potential is the minimum energy required to remove an electron completely from the molecule, right? That becomes smaller. Ionization potential. Right, you can imagine if you excite an electron to the first excited state to go to the, to the vacuum energy, that is a much smaller distance when it's excited versus when it's in the ground state. And that also then means that you have a greater electron affinity. So the electron released when an electron comes from outside of the nucleus of the molecule to occupy a lower lying available orbital that is called the electron affinity, and that becomes greater when you promote an electron to the first excited state. Okay, so what's the result of that? Is that you have very different redox properties. Okay, so often you start with a complete transfer to or from the excited state. So what does that mean? Let's look at that. So let's say we have a molecule A. We excite it with light, H nu, right, to the excited state. So I use this asterisk to indicate excited state. Then I add another molecule B, for example, which in this case does an electron transfer. So I can make, for example, a radical cation, a radical anion, or, I mean, it depends what the nature of A and B are, or I can have the radical anion on A and the radical cation on B. Okay. Okay. Another result, which is interesting, of photochemical reaction is that you can selectively excite just one molecule, right? So let's say you have a reaction, and with light you can hit a molecule and, for example, not hit the solvent or anything else. So if you compare that to a thermal reaction, where you hit everything, you give energy to all species. So substrates, solvents, products. Okay. I already told you this, but let's look at it in detail. Photochemical reactions are mostly irreversible. Okay. So if I go from A, H nu to H star to the excited state, and I go to B, then I will not be able to go from B back to A star. Okay, this is just simply impossible. There is a special case, of course, which we've already looked at. So if you imagine, for example, azobenzene, you can go from the cis to the trans form using light. So I put H nu1 or temperature, and usually with a different wavelength, H nu2 or temperature, I can go back. But this is not an equilibrium, right? These are two photochemical processes that go through different excited states. So often the spectroscopic properties of A and B are different, right? So the absorption spectrum, the emission spectrum will be different. And so this is called a photostationary state. Previously it was called photoequilibrium, but that's wrong. Okay, so don't use that. It's not an equilibrium. It's really a steady state, which is quite different, right? An equilibrium, when you stop, for example, the light, an equilibrium would stay in the same spot, right? A stationary state, in this case, if we stop the light, the system will change, right? But it's not the same. Okay, so this is a special case. Okay, so let's look at some numbers. Okay, so we have the photon energy, which is E, it's h times nu, right? So this is Planck's constant, which is 6.62 times 10 to the minus 34. So the units are meter squared kilogram per second, or joule times seconds. And this is the frequency of the light, which can be 1/seconds, which is hertz. Okay. Up. Or, of course, more commonly is the wavelength, lambda, which is the speed of light over nu. Okay, so let's look at some values. Okay, so if we put nu here in second minus 1 times 10 to the minus, this should be 15th, no, 15th, yeah. Lambda in nanometers, or energy in kilojoule per mole. So if we are in the far UV, this is 3.0, 100, 1200, so 1200 kilojoule per mole. So that's an awful lot, right? UV, you're in this range, 1.2 to 0.86, 250 to 350 nanometers. Still a lot of energy. If you're in cyan, so between blue and green, 0.6, 500 nanometers, 40. Red, energy is going down. So we're at 700 nanometer light, 171, and then you have near infrared, 0.3. Wavelength is about 1000, and the energy is going down. Okay, so these are some typical energies that are involved in these processes. And then we have, probably everyone knows this, the Beer-Lambert law, right? So that says that the absorbance, D, is epsilon times concentration times length. And that is the log of the incident light over the transmitted light. Okay, so absorption coefficient here, which is in per molar per centimeter, concentration in molar, path length in centimeters. So just imagine you have a cuvette, you have some light coming in with some intensity I0, Some light will be absorbed, the rest will be transmitted, which is I. My solution. And that's Beer-Lambert law. Okay, so that's kind of important. Again, this breaks down if you use very intense laser light. You can have problems with that, or at high concentrations, you can have, for example, a molecule that absorbs, it emits fluorescent light, which is again partially absorbed by the same molecule. So this law is not always linear for all conditions, but typically it works reasonably well. Let's look at a typical spectrum, right? So probably you have measured some absorption spectrum of some molecule in the past. So we would have absorbance, which has no dimensions, right? On this axis, and we put wavelength lambda nanometers on this axis, put some values, let's say 200, 250, 300, 350. So if you measure a molecule, it will typically have some, I don't know, some features like this. And that is always kind of broad, right? If you measure a molecule, the spectrum is broad. You have broad bands for a molecule. And that is because you have many vibrational and rotational energy levels. Okay, if you would, I don't know if you've ever measured the absorbance of an atom, like a salt or something, it will have these kind of very sharp, whatever lines like that. So atoms don't have all these vibrational levels, so they give very sharp transitions. So the benefit for having broad bands is that your excitation wavelength, so lambda excitation, does not need to match exactly to a narrow electronic configuration. Right, so you use some kind of wavelength of light because you buy, you know, a lamp and use filters, or you use LEDs or use a laser. Those typically have a pretty narrow and well-defined wavelength. And so if you have only very narrow absorbances, it might be difficult to exactly tune your light source to that system. So that's actually a benefit. So if we look at some of these transitions, then we have the most intense ones are pi star transitions that have an absorption coefficient of about 5,000 to 100,000 per molar per centimeter, and less intense you would have an sigma star transitions, which are, let's say, 100 to 1,000 per molar per centimeter, and N2 pi star would be 1 to 400 per molar per centimeter. Okay, so let's look, for example, for an alkene. If we draw the energy. Have something like this. So we have the sigma orbital, pi star, sigma star. And so let's fill this up. So this would, for example, be the triplet excited state. Right, remember, look at these two electrons are parallel, which is repulsive, which lowers the energy, which is the triplet state. Okay, so that is good. So let's say once we are in the excited state. Okay, so once we're in the excited state, we can have a range of photophysical processes. Okay, so we can split them up into different sections. One is radiative processes, and the other is non-radiative processes. So I'm going to call this one radiative. So those are luminescent processes, which means a photon is emitted. And of course, the most famous one of those is fluorescence. Okay, so what is fluorescence? You are in a singlet excited state, and you relax to the ground state. And this is without flipping the spin of the electron, and that's called spin allowed. Okay, so this is usually from the lowest excited state. And then there's this rule, which is called Cash's rule, that you have non-radiative processes or decay processes from higher states. It's much faster. So even if you excite with a higher energy than you need to reach the first excited state, so you're in a higher vibrational state, you have this very rapid non-radiative decay, so without emitting a photon. And then once you reach this lowest first excited state, then you go down, you emit a photon, and you have fluorescence. Okay, so fluorescence, that's a big benefit, can be done with extremely small amounts of material, right? So even nanomolar or lower, concentrations, you can still get a decent signal with fluorescence. which is why it's so popular, well, in spectroscopy, but also in imaging. So fluorescence microscopy, confocal microscopy is relying purely on fluorescence. So fluorescence is typically measured at room temperature and in solution. Often people degas their solution because you can have photochemical reactions with oxygen. Or if you excite a solution that, let's say you're in water, you have some dissolved oxygen, you shine UV light on that, you make singlet oxygen, and that's pretty reactive. So often there's, if you really want to do quantitative measurements, people will degas their solutions. And for water, the most efficient one is to do what's called freeze, pump, thaw cycles. Freeze, pump, thaw. So that means you make ice, you put it on a vacuum line, then you let it warm up again, and then you repeat this, multiple times, and that is quite efficient to remove oxygen from solutions. And fluorescence can be quantified by the fluorescence quantum yield, which is this, which is the number of photons emitted over the number of photons absorbed. Okay, and this has a range, of course, which is typically from 0 to 1. And another interesting parameter is the fluorescence lifetime. And so that's the typical decay time of fluorescence emission after stopping the excitation. Okay, so typically those singlet lifetimes are very short, so picoseconds to nanoseconds. Okay, that was fluorescence, right? That's the most important process typically. But a second one, right, that's also still radiative, is phosphorescence. So what is phosphorescence? It is the lowest excited triplet state that decays to the ground state. And so the spin needs to flip. Right, if we look again here at this diagram, so you can see if you are in this pi star triplet excited state and you want to go back to the ground state, the spin has to decay, but it also has to flip to fit back in the ground state. And so that's energetically not very favorable. So that is called spin forbidden. Okay, that is typically, it's measured in bulk at 77 Kelvin, so very cold, in a glass matrix. or maybe glassy, not glass, the material glass, but in a glassy matrix. So it's really fixed. And those lifetimes, so the phosphorescence lifetimes, they're in the microsecond to minute range, right? So much, much, much slower or much longer lifetimes than the typical fluorescence lifetime. So when people measure those properties, for example, they will give an excitation pulse, really short pulse of light, something like femtosecond, and then they will measure in time the photons that are released from the material. So you will have first a burst of fluorescence typically, and then much later is followed by light that comes due to phosphorescence. Okay. So then we have non-radiative processes. So that means no photons emitted. And again, we can split this into two branches. So one is you have no spin change. And that is called internal conversion. So that is rapid decay to the lowest excited singlet from a higher excited singlet. And you have similarly, so you have rapid decay to the lowest excited triplet from a higher excited triplet. Okay. Then you have processes where you do have a spin change. Some color here. No spin change. Spin change. And that is called inter-system crossing. Okay, so let's look at a convenient way to visualize all these processes, and that is using it's called the Jablonski diagram. Okay, so this is the Jablonski energy diagram. So we have the different states. We have the singlet, so S0 ground state. We have the first singlet excited state, S1. So those are the thick lines are, let's say, the real states, and these thinner lines are all the small vibrational states that are close to that state. So we have the second singlet excited state, and we have an excited triplet state T1 here. And so this little simulator allows you to see all those processes. So let's walk step by step through the different processes that we already discussed about to see a bit, how we move through this Jablonski diagram and what are the typical time scales. So for every step, it will show the time scales. You can already see that fluorescence, so internal conversion and vibrational relaxation. So those are extremely fast. Excitation is also extremely fast. Other ones depends a bit, they can be slower. Okay, so let's look at fluorescence. There we go. So we excite from the ground state to, for example, the second excited state, you have vibrational relaxation, internal conversion, again, vibrational relaxation, and then fluorescence. Okay, then you end up in some vibrational state, again, vibrational relaxation. Okay, this was maybe a bit fast still. Okay, let's look at fluorescence quenching. So this means that from the first excited state, you will transfer the energy to a quencher, and so there will not be emission, right? So again, we excite from the ground state to, again, second excited state. This depends a bit on the wavelength I select here at the bottom, okay? Then once we are at this lowest excited state, the energy is transferred to a quencher, so we have no emission, and we end up in the ground state. Okay, this is the most boring one, so non-radiative relaxation. So we get excitation again. So we go to the second excited state, vibrational relaxation, internal conversion, again, vibrational relaxation. And then we basically have non-radiative relaxation. So you show that with this squiggly line instead of a straight line in the Jablonski diagram. Okay, let's look at phosphorescence. Let's see if we can put a little bit less energy light. So we just go to the first excited state. Not sure if this is going to work. So we excite and we reach, yeah, we stay in the first excited state. And we relax, we get intersystem crossing, again, some vibrational relaxation. And then we get phosphorescence. So you saw the time scales 10 to the minus 3 to 10 to the second, so 100 seconds. So extremely slow relaxation, and thus, you can have a very long emission of light, even after a very brief excitation pulse. Okay, triplet non-radiative relaxation. Again, always start with excitation to the singlet excited state, goes to the lowest singlet excited state again, intersystem crossing, relaxes within the triplet state, and then we have the very boring non-radiative relaxation back to the ground state. So no light is coming out of your system. This one is kind of interesting. It's called delayed fluorescence. So let's see what happens. So we excite to the singlet excited state, vibrational relaxation, very, very, very fast to the singlet excited state, intersystem crossing, and immediately back. And then we get, again, it's called phosphorescence, but it's more delayed fluorescence because you get the wavelength that is associated with the fluorescence, but because it first went to the triplet state and then back to the singlet excited state, when these energies are not too far apart, then you can have a very long of this wavelength, right? Because the wavelength is determined by the difference in these energies, but because it went to the triplet excited state, it could take very long. Okay, so let's go back to the slides. Okay, so we're back here. So in the last part, I just briefly want to talk about, these are, I talked mostly about photophysical processes. Let's now look at what's really relevant. So we have photochemistry relevant to kinetics. This is, after all, a kinetics course, mostly. So if we try to summarize the most important processes, and I will, maybe I can first show you that. So I will put on Moodle an overview of all these processes. Let me first briefly go there. So this is a list of these photophysical and photochemical processes. So it starts always with absorption, right? So the ground state is absorbing a photon, giving the first excited state. And then you can have all these physical processes. So in the singlet state, so there's a 1 in front of the molecule. So this is the singlet excited state, internal conversion to the ground state. Okay, then, you know, this is just a summation of all the processes we have already seen. So fluorescence, intersystem crossing, you can have multiphoton excitation, quenching. Then you have processes for triplet states. If you want to go all crazy, you can have a first excited state can interact with the second molecule, giving what's called an excmer. So if that happens with itself, then you call it excmer. If it happens with another molecule, B, then it's called an exciplex. We can have energy transfer, quenching, and then we can have electron transfer, ionization, photochromism, all these kind of things. Okay, so I will put this on Moodle. This is just, it's not the only things that can happen, so it's an incomplete list, but it's already quite a long one. But again, to come back to my main story, let's look at the processes that are really important in chemical kinetics. So when we do photochemistry, which of those processes are really important? Okay, so imagine we start with a molecule, which we'll call AB, and it's in the singlet excited state, right? And this is a molecule. Then let's look at different processes. So we had seen already going to the triplet state, right? So this is intersystem crossing, ISC. We can have fluorescence. So we have AB plus H nu accent. So the accent means that it's an emitted photon, to distinguish it from just H nu, which is an absorbed photon. And we have what's called a B, so we can have quenching, or we have energy transfer to a quencher. It's called Q. And then let's look at some real photochemical processes. So an important one is bond dissociation. So A and B split into AB, both radicals. And we can have charge transfer. So that leads to a complex A plus B minus that, depending on the solvent, can then dissociate in A plus plus B minus. Okay, so let's look, let's give it some numbers. So we'll look first at bond dissociation, then at charge transfer, and then at intersystem crossing. Okay, so fluorescence we've already seen, so let's look at some chemical examples. Okay, so for bond dissociation, for example, iodine with light would split into two iodine radicals. Okay. charge transfer example. Iron 3 chloride with light, which gives first this iron 2 plus chlorine radical complex, which falls apart in solution to iron 2 plus plus chlorine radical. Okay. Intersystem crossing. Let's say we have this compound, right? Benzophenone. So benzophenone, CO phenol. Okay. So that first absorbs a photon. So we are in a singlet state. Oh, you don't. Then we go to a triplet excited state. And then that triplet can react with isopropanol, which really is quite an unreactive species. You know, isopropanol is a very common solvent, and that leads to these two radical species. Okay, those are some examples. So how can we quantify these reactions? So again, you use the quantum yield of the reaction, right? Quantum yield is number of product molecules divided by number of photons absorbed. And if we multiply both sides with Avogadro, we get the moles of product divided by Einsteins. So Einsteins are units, actually. And so the range of this quantum yield is again 0 to 1. Of course, there are again some exceptions because you typically have a form of losses. Right, so for example, if you make radicals, they can often react with a solvent. Right, so you did excite your molecule, it did split into two radicals, but you don't form any product from that radical reaction because your radicals are already scavenged by your solvent. Another issue, it's kind of a bookkeeping issue. So in the gas phase, so for example, this iodine splitting to two radicals, that is one photon gives two radicals. So if you don't define your quantum yield correctly, you can get a quantum yield higher than 1, which would be strange. And it's even worse if you have, for example, a chain reaction where you have one photon, that gives one radical or two. And that gives a whole lot of polymer. polymer. So if you would quantify, your quantum yield as that, you have number of product molecules would be quite enormous, right? Or versus the number of photons absorbed. If you would do it by mass, for example, if you would just weigh your yields out at the end. Okay, last important point is on fluorescence quenching. Okay, so let's repeat again the most important processes that are involved. So we have a molecule which is excited by light, giving the excited state. We have the excited state, which can, with some rate, fluoresce back to the ground state plus H nu accent. Okay, so this is fluorescence. And we have our non-radiative decay. Oops, back to the ground state, so Kg back to A. So this is non-radiative decay. So these are the normal processes. If you don't have any quencher around, these are the processes that typically happen. So now if you add a quencher, Q, then so we say, okay, we have the first excited state plus quencher with a rate kq, and that will go to the ground state plus the quencher is in the excited state, so it's energy transfer. Okay. And then you have Q that relaxes to the ground state, again, non-radiative. Okay. Oops, let's leave it like that. So let's write some rates. So let's write the rate for the excited state. And now I'll say that's the quantum yield times the light intensity. So that's for this first process here, right? That's this one. And the rest is quite like you're used to. So we have the disappearance of the excited state because of Kf, because of fluorescence. We have minus Kg times A star. And we have Kq times A star times Q. All right, let me see if I can just color those things. So this is this process, right? This is non-radiative decay. It's this one. And this process is this rate. Okay, so let's do steady state. Steady state approximation. So we can write star is the first process, so excitation over Kf plus Kg plus Kq times Q. Okay, so what can we actually measure? What we can measure is the intensity of fluorescence. Fluorescence intensity in absence of quencher Q, and then we can add quencher, so call it IF, which would be the fluorescence intensity in presence of quencher Q. Okay, so if we write that out, we can do measurements where we measure those differences. Okay, sorry, I hear there's some question. Oh, quenching, yeah. It's not a person quenching, it's a process, right? Okay, there we go. Times IA over KF plus KG over, try to make this line a bit longer. Up, IA over KF plus KG plus KQ times Q. Right, so this is the rate, the concentration of A star that we just derived, right? So that comes from here. And the same thing, if you have no quencher, then this term falls out, KQ times Q. So that is the top denominator. Okay, that's a bit ugly. So if we simplify this, the whole excitation term just falls out, and we have KQ over K, so fluorescence plus non-radiative decay times Q. So if you look at these two terms, that is actually the fluorescence lifetime, or it's 1 over the fluorescence lifetime. Right, because if you have fluorescence and you have non-radiative decay, those two together is what you would actually observe in terms of photons, and that is the fluorescence lifetime. So we can write this whole thing as 1 plus KQ times fluorescence lifetime times Q. And so either this this notation or this notation, this is called the Stern-Volmer equation. Okay, so how would you measure that? So it's quite simple, right? I would measure this intensity of fluorescence in absence of quencher over intensity of fluorescence in presence of quencher, and I would do that at different quencher concentration. And so when the quencher is 0, this is of course 1, and then this will just be, whoops, a linear plot where you would make some different measurements, right? So and that allows you to actually extract also the fluorescence lifetime.